Hi everyone, this is Dr. Swaminathan SM. Now the topic is lead lag compensators under the Unit 3 Frequency Response Analysis. So the outline of today's topic is review about the previous class. So last class we discussed about the series and parallel compensator. Here we are going to discuss about the lead compensators and rules to design the phase lead compensation and lead compensator realization using frequency response analysis, and the following to the activity introduction about the lag compensators and lag compensators realization, frequency response, and determination of omega m and pi m. Following with this summary. So next, the lead lag compensators introduction. So the lead compensator is an electrical network which produces a sinusoidal output which is having phase lead when a sinusoidal input is applied. So if you are applying the sinusoidal input, it is lead. So in order to produce the phase lead at the output of this compensator, the phase angle of the transfer function should be positive. So lead means that is phase angle, transfer function is positive. Just opposite, the lag compensator means it's an electrical network which produces a sinusoidal output having the phase lag when a sinusoidal input is applied. So in order to produce the phase lag at the output of this compensator, the phase angle of the transfer function should be negative. So lead means positive, lag means negative. Just to make the comparison, so I bold the comparison between the lead compensator and lag compensator. Maybe this will be considered for the lead lag compensator. So first, the lead compensator, the three design rules for the cascade compensator. The first one, the design is stable with the satisfactory steady state error, but dynamic performance is not good enough. Compensator that is used to change the medium and high frequency parts to change crossover the frequency and phase margin. Next, second point, the system is stable with the satisfactory transient performance, but the steady state error is large. Compensator is used to increase the gain and change lower frequency parts, but to keep medium and higher frequency parts unchanged. And third point, if the steady state and transient performance are either unsatisfactory, the compensator should be able to increase the gain of the lower frequency part, the change of the medium and higher frequency parts. So here look at the transfer function of the lead lag for RC, because mostly for electronics we are using only the RC. If electrical means we are using the RLC. So look at this R1, R2, that is in the series mode, and R1 parallel with the capacitor C. Then you can get the transfer function GC of S, that is output divided by input, E naught of S divided by EI of S. So equal to 1 by infinite into 1 plus infinite Ts divided by 1 plus Ts. So where alpha, that is R1 plus R2 divided by R2, that is greater than 1, then T, that is because both are in the parallel condition, so T is equal to R1 R2 divided by R1 plus R2, this C. So look at these poles and zeros. So poles means that is a cross symbol, that is X, that is called a pole, and zeros means that is a round symbol, that is called the zero. So rules to design the phase lead compensation. First, determine the K, satisfy the steady state error constraint, and second, determine the uncompensated phase margin pi naught, and third, estimate the phase margin pi m in order to satisfy the transient response performance constraint, and fourth point, determine the alpha, and fifth point, calculate the omega m, and sixth, determine the T, and seventh point is the confirmation. So the lead compensator, it is a compensation that is having the characteristics of a lead function. So the lead compensation increases the bandwidth, which improves the speed of the response. It improves the transient response, but the small change in the steady state accuracy, and it has high pass filter, like the high pass filter. So S-plane representation, S plus ZZ, that is S plus 1 by T, and S plus PC, that is nothing but poles, that is S plus 1 by alpha T. Just remember, transfer function is equal to zeros divided by poles. So the zero of compensation ZC is equal to 1 by T, and the pole of compensation PC is equal to 1 by alpha T. So T is equal to 1 by ZC, and its alpha is equal to ZC by PC. So look at the zeros and poles for the lead compensator. And the realization of the compensator, look at this, the realization, that is R1 and the capacitor is both are parallel. So you can like 1 by SC is the capacitor. So, and again R2 is the another series capacitor. So R into 1 by SC, that is both are parallel condition. So R1 plus R2 divided by R2. So you can like R2 divided by R2 plus that parallel combination means R1 R2 divided by R1 plus R2, that is the compensation. Here we are using the capacitor means that is 1 by SC. So you can write R1 into 1 by SC divided by R1 plus 1 by SC. So say same thing for E naught. E naught means nothing but that is the divider rule you are applying. Ei of S, input signal, that is input signal, input voltage. Just a reminder is the voltage. So Ei of S into R2 divided by, that is R2 R2 value is plus with the R1 divided by R2CS plus 1. So you can just reduce the value, you can get the output divided by input, that is a transfer function. So T is equal to R1C and alpha is equal to R2 divided by R1 plus R2. And the frequency response GC of S, that is equal to S plus 1 by T divided by S plus 1 by alpha T. From this you can get the put S is equal to J omega. To convert, you just substitute the value S is equal to J omega to convert S domain into frequency domain. So you can get omega C is equal to 1 by T, omega C3 is equal to 1 by alpha T. So for magnitude, you can find the magnitude 20 log root of 1 by 1 plus omega T the whole square divided by 1 plus omega T the whole square root. So from this you can get the frequency response of the lead compensator for phase angle and the margin, that is the gain margin. So first the x-axis will be the different omega value, that is angular frequency level omega C1 and omega C2, and you can get the pi value. Pi is nothing but the phase angle, tan inverse omega T minus tan inverse omega alpha T. So omega is equal to 0 means pi is equal to also 0. Omega is equal to infinity means pi also infinite. So based on this you can draw the frequency response of the lead compensator, and again the determination of omega m and pi m. So omega, that is pi is equal to phase angle, that is pi is equal to tan inverse omega T minus tan inverse alpha omega T. So the differentiation with respect to omega and equate to 0. So you can get omega m is equal to 1 by T root alpha, and pi m is equal to tan inverse 1 minus alpha divided by 2 root alpha. So following with the activity, you will see the lag compensation, same like for lead compensation. So the lag compensator, that is having the characteristics of lag networks, it improves the steady state performance but results in the slower response due to reduced bandwidth. So it is especially a low pass filter. So lead compensator, high pass filter, this one is the low pass filter. So again the same thing for S-plane representation. So using the S-plane representation, look at this, the x-axis, y-axis. X-axis you are mentioning the zeros and poles, and y-axis means j omega, that is a frequency domain. So for the zero lag compensator and pole compensator, 0 means that is 1 by T and pole means 1 by beta T. So beta is nothing but ZC divided by PC. So you can get the lead compensator, and the realization same thing. So R1 R2, that is both are in the series compensation, and 1 by SC, that is the capacitor that is connected with the series. Lag means, you just remind, it is a series, and lead means nothing but it is a parallel. So R1 parallel with the capacitor means that is lead, series means lag. Same thing, you just make the realization means reduce the network, and you can get the output divided by input transfer function, and substitute the value T beta. So S is equal to J omega to get the frequency response of the lag compensation, same like lead compensation. If DC gain of the compensator is not desirable, beta can be eliminated. So you can get GC of J omega, and just substitute the omega C value, C1 value, omega C2 value for crossover frequency, and make A is equal to, that is the gain, modulus of GC of j omega 20 log root of 1 plus omega t the whole square divided by 1 plus omega beta t the whole square. So at low frequency it is less than 1. So that is equal to 0. Frequency ranges from omega c1 to omega c2, that is omega t less than or equal to 1, less than 1, and omega beta t greater than 1 means A is equal to 20 log 1 divided by root of omega beta whole square. So you can get 20 log 1 divided by omega bt. So at high frequency, that is greater than 1. So you can get the omega t the whole square divided by omega beta. So you can get the 20 log 1 by beta. So for three different frequency range, is just a reminder. First one, at low frequency it is 0, and high range of frequency, that is third one, 20 log 1 by beta, and third one, that is omega c1 to omega c2, between the ranges between omega c1 omega c2, that is 20 log 1 divided by omega beta t. So this is the different gain. And next, that is the marginal gain, and next pi, that is the phase angle, tan inverse omega t minus tan inverse omega beta t. So the A is equal, omega is equal to 0 means pi also 0, omega is equal to infinite, pi in the, that is 0. So you can get the phase angle, that is frequency response analysis, omega m root of omega c1 c2, and again you just substitute the omega c1 c2 value here, then you can get 1 by t root of beta. So determination of omega m pi m, that is the same thing for lead compensation. So the frequency omega m, that is determined by the differentiated with respect differentiated pi with respect to the omega, then equal to 0. So t pi divided by t omega is equal to 0. Then gc of j omega is equal to pi tan inverse omega t minus tan inverse omega beta t. So again differentiation, and you make the differentiation for the tan. So the formula d by d theta into tan inverse of theta 1 by 1 plus omega 1 plus theta squared. So the same, like instead of theta it is having omega t. So 1 divided by 1 plus omega t the whole squared into t, and again 1 by 1 plus omega beta t whole squared into beta t. So based on this, omega is nothing but omega m. So just substitute the value omega m. Then based on this, just equate the denominator value, same thing here. So left hand side denominator value and right hand side denominator value. Then you can get the omega m is equal to 1 by t root of beta. So this is called the lag compensator. So from this you can get the pi is equal to that phase angle tan inverse omega t minus tan inverse omega beta t. So tan theta, tan of tan inverse omega t minus tan inverse omega beta t. So from this you can get the formula tan a minus b, tan a tan b minus tan a tan b divided by 1 plus tan a tan b. So from this you can just substitute the value omega is equal to omega m, theta is equal to pi is equal to pi m. So you can get pi m is equal to tan inverse 1 minus beta divided by root 2 root of beta. So this is called the lead compensator and lag compensator. Thank you.